In the previous video, we controlled this Raspberry Pico using raw Bluetooth packets from a generic Bluetooth application. Today we are building a proper controller, a React web application that runs in Chrome, and let us drive the Pico with the keyboard. And the whole app will be generated using spec-driven AI development for just $3.20. The Pico already exposes a Bluetooth interface. It accepts simple byte commands to control the motor and the steering servo, but sending raw bytes from a mobile debugging application is not a great experience. For the system overview, here is how everything is connected and how the control protocol works. At the center of the system is the Raspberry Pico. The motor is connected to the Pico through DRV8833 motor driver, which handles the motor control signal safely and let the Pico to command forward and reverse motion. The servo is also connected directly to the Pico, so Pico controls both movement and steering. On the software side, the Pico is running FreeRTOS. For Bluetooth, all the BLE-related code is currently stored in a file called ble.c. My plan is to provide this file to the AI as additional context, so it can understand exactly how Bluetooth is already implemented in the firmware. The communication protocol itself is intentionally very simple. Each command is just 3 bytes long. The first byte controls the motor, the second byte controls the servo, and the third byte is reserved for future use. All command values are in the range from 0 to 200. For the motor byte, a value of 100 means stop, a value of 0 means full reverse, and a value of 200 means full forward. For the servo byte, a value of 100 means the setter position, a value of 0 turns fully left, and a value of 200 turns fully right. So overall, the web controller only needs to send very small packets: 1 byte for throttle, 1 byte for steering, and 1 extra reserved byte. So for the controller, I've decided to build a small web application using React. The key thing that makes this possible is that modern browsers, especially Chrome, support the Web Bluetooth API. That means a website can communicate directly with Bluetooth devices without needing a native mobile application. For building the application itself, I'm using a tool called Kiro. Kiro focuses on something called spec-driven development. Before we start building the app, I want to briefly explain what spec-driven development means. Most people interact with AI coding tools in a prompt-by-prompt way. You type a prompt, the AI generates some code. Then you notice something missing, so you write another prompt. Then another and another one. Each step works, but the AI only sees the current prompt and limited context, so the overall structure of the project can slowly drift. Spec-driven development takes a different approach. Instead of immediately asking the AI to write code, the process starts by writing a requirements document. This document describes what the system should do. For example, in our case, it might describe things like connecting over Bluetooth, sending control packets, and responding to keyboard input. Once the requirements are defined and validated, the AI generates the next layer, the design document. The design document explains how the system will be built. It defines things like architecture, modules, and interfaces. From that design, the AI then generates a task list. These tasks break the project down into small, concrete implementation steps. Instead of one giant prompt, the AI works through the tasks one by one. As each task is completed, Kiro provides progress updates and moves to the next step. The big advantage here is that AI always sees the full context of the project, the requirements, the design, and the overall plan. That makes us much better at handling larger projects, because the problem is broken down into structured steps instead of a long chain of prompts. So in this video, we'll start with the requirements, let Kiro generate the design, and then watch it execute the tasks to build the controller application. To get going, we are going to create a new ReactJS application in a command line. And we're going to use ChatGPT to help us with the right command. After the application is created, we are going to copy Bluetooth implementation from our Pico to a folder inside the app. This way we can provide this file as a context to Kiro. Now we can open project folder in Kiro and start using spec-based development. We are going to provide our initial prompt. We are going to include details about Bluetooth, including the Bluetooth implementation from the Pico. This way, Kiro can pick up all the context required to connect to Pico. In addition, we're going to provide details around our protocol and in general how we want our application to behave. Kiro is going to take this prompt and turn it into a requirements document. We don't have to capture everything in a single prompt. In general, creating a requirements is a set of iterations. Now Kiro has generated the requirements document, and at first glance it looks pretty good. But before moving forward, I want to refine one of the requirements. Right now the document suggests sending a Bluetooth packet only when a key is pressed. That would technically work, but it's not ideal for this type of system. Instead, I want the controller to send a packet every 250 milliseconds, regardless of whether the input has changed. The reason for that is safety. If Raspberry Pico stops receiving packets for some amount of time, it can assume that the connection was lost. In that case, the Pico can trigger a fail-safe behavior, like stopping the motor. It's really important for something like an RC car, because we definitely don't want the vehicle to keep driving if the controller disconnects. So I'll update the requirements to make sure the application sends control packets periodically every 250 milliseconds instead of only reacting to key presses. Once the change is in place, we can move to the next step. Everything looks good, and we can move to the design step. And after the design document is done, we can ask Kiro to generate tasks list. When ready, we can execute all essential tasks and let the Kiro do its magic. And after 40 minutes of work, looks like the application is done and we can give it a test. Now that Kiro has finished executing the tasks, we can take a look at the generated application. On the screen here is the React web app that was created from the specifications. At the top we have simple connect and disconnect buttons. This allows the browser to establish a Bluetooth connection with the Raspberry Pico using Web Bluetooth API. Right next to that, the app shows the current connection status, so it's easy to see whether the controller is connected or not. Below that, there is a short section explaining which keys to use on the keyboard to control the vehicle. This makes the interface very good, and you don't have to remember the controls. So overall, the generated application gives us everything we need: Bluetooth connection controls, keyboard input handling, and a clear view of the command values being transmitted to the Pico. Let's quickly talk about the cost of generating this application. On the Kiro pricing page, you can see that the additional token cost is 4 cents per token. For this project, the full process, generating the requirements, the design, and executing all the tasks, used 80 tokens. So if you multiply that out, the total comes to $3.20. And that's essentially the worst case scenario. Kiro actually offers different usage tiers, and depending on the plan you're using, the effective cost can be lower. There are also free credits available, which can offset part of the cost when you're experimenting or building small projects like this one. Alright, let's try it out. Once connected, the connection status updates and the controller is ready to go. Now we can use keyboard to control the car. The motor value changes when I press forward and reverse keys, and the servo values changes when I steer left or right. And we can reset both values. The app is sending control packets every 250 milliseconds, so the Pico always knows the current command state. If the connection drops or packets stop arriving, the firmware can trigger the failsafe and stop the vehicle. So this gives us a simple but pretty robust way to control the car directly from a browser. No installation, no mobile app, just a small React page and Bluetooth. And that's the whole system working end to end. In the next video I'll switch gears a bit and work on the mechanical side of the project. I'll create a 3D model in FreeCAD, which will be used for the chassis and mounting the electronics.